Uh, Good morning, everyone, and I want to welcome you to the new week. Before I get started today, I want to make an announcement. Particularly, I'm going to start with the syllabus. Uh, why am I displaying this today? Is because I've edited the syllabus. Uh, if you look at, we are in the week of, March 21 to March 25. So which means the focus this week is basically going to be on chapter 8, which we call the additional topics in analysis of variance. Now, I actually realized that 3 lectures is not enough for you to be able to comprehend chapter 8. Because of that, we're going to have 4 lectures in chapter 8. The fourth lecture will be on Monday, next Monday, March 28th. Okay, so that is the reason why you are seeing that. And of course, the exam 2 preview will basically be on next week, Wednesday, where I'm actually going to walk you through the practice exam questions. And of course, April 1, the exam 2 is basically going to be written on April 1. So that is what I want to show you, to just tell you that I've already modified the syllabus. Okay, another information that I want to give today, it has to do with a practical assignment. Now, on the practical assignment, I've already graded assignment 1, practical assignment 1, which is just you telling us your topic that you want to work on, that has already been approved. Okay. Now we are on practical 2 now. And what is the instruction? Okay, for practical 2, there is no any special requirement. All what I just want to say is for you to import your data set into the practical 2 part. Uh, you know, the analysis and whatever you're going to do, that will be practical 3. In practical 3, I'm also going to release a detailed instruction on maybe the number of pages, the minimum number of pages, and so on like that. Of course, that would be, contained in the instruction for practical 3. But what I need at this time, what I need is just for you to import your data set. I just want to say, okay, when you are using a data set from online, make sure you write the source, okay? Whichever way you get your data, I actually need information about the source. Is that okay? Do you understand that, everyone? Okay, so there's no any special requirement. And you know what? If you choose a topic before and you realize that you're not able to see data set, you can actually change your topic. You are not going to lose your practical 1 grade. But what I just want to hear from you, you need to tell me if you've changed your topic. You can include that, you can include a message in your submission, okay? Because I'm also going to see, is there any agreement between the data set you actually importing and the topic you've submitted before? Okay, I just want to see, because in a situation where there is no agreement, okay, you could lose some point, and I don't want everyone to lose a point. So if you are changing your topic, make sure you include that information in your submission. Okay, those are the information that I have for you today. But before I move on, I'm also going to say this. Some of you have reached out to me about extending the practical, the ongoing assignment. A lot of you have seeking for extension, and because of that, I think I've considered that. But I also want to tell you a new assignment will be uploaded today, but I can extend the deadline of the ongoing one by 48 hours. Okay, I'm going to effect that today. So the ongoing assignment, the deadline is going to be on Wednesday. So that is on popular demand. But a new assignment will be uploaded today as well. Okay, give me 1 second while I pull up. And I also want to tell you the material for this week. They've already been uploaded. You can check online. You're actually going to see that. Okay, so I want to welcome you to chapter 8. Give me 1 second. Let me adjust this. Okay, I want to welcome you to a new chapter that we call chapter 8. And this topic is called additional topics in analysis of variance. Of course, you've been introduced to analysis of variance in a situation where we are trying to compare means in more than two groups. We are basically going to have one response variable, which is continuous, and we're going to have a categorical factor. When you have one categorical factor, you have one way ANOVA, right? When you have two categorical factors, or you have two way ANOVA, we could also have situation where we could have two way ANOVA with interactions. I think I will walk you through that. Okay, so but what is new? What do we want to do today? Basically, today's we basically want to focus on number one. How do we actually investigate whether certain assumptions are met or not? Because every statistical model, okay, has assumptions, okay? And you know what? Before we can actually rely on, recommendation from our finding or given by particular model, we actually need to have a way to validate the model. And the way to validate the model is basically to subject the model to diagnostic testing. What do I mean by diagnostic testing is probably revisiting whether assumption hold or not. And you know what? In the outline, I'm actually going to walk you through how can we investigate whether the assumptions of homogeneity or variance hold. That is going to be outline number one. I'm conducting analysis of variance. One of the assumptions is that there should be constant variance across groups. Okay, how can we actually tell whether constant variance exists? Okay, we have different kind of tests that can be conducted, for that. But today I'm going to walk you through Levini test. The other time I show you a Bartlett test, but today I'm going to show you how the Levini test work. Now, after that, the next thing we basically want to do is this. It is not only the assumptions of constant variance that needed to, be a whole in the analysis of variance. Don't forget, we also need the assumptions of normality, but we don't have any issue with that. When the normality assumption failed to hold, of course, you know what we did last week. What we did last week is an attempt to fix the problem of normality. How do we fix the problem of normality? We perform transformation, right? I walk you through that, where we transform the response variable, where we did the log transform, the square root transform. We also use a Tukey transform and the Boscos transform. The approach, what we did on the transformation is basically to fix normality problem. Okay, now, and that is the reason why today, one of the focus is going to be on, how to investigate whether constant variance assumption hold or not. Now, another outline for today is this. When we conduct analysis of variance tests, if the null hypothesis is rejected, I'm going to say that again. If we reject the null hypothesis, why? Maybe, probably, the p-value of the test is very, very small, it's less than a given level of significance, of course, we're basically going to reject the null hypothesis. But you know what? One of the weakness of the analysis of variance is that the analysis of variance will not tell us where the difference lies. Therefore, for us to be able to, figure out where the difference lies, we basically need to, conduct what I call a multiple comparison test. Okay, so I'm going to show you, how to do that, even though we've done that before. But you know what? Part of the discussion today, we have different kind of multiple comparison tests, like Bonferroni, the Fisher LSD, and Turkey test. Then I'm going to tell you which one should we use in a particular situation, because there's also limitation, when you are talking about the multiple comparison test. Then at the end of the day, you're basically going to see how we make inference. Now let's get started with the testing for assumptions. Assumption of what? When I say homogeneity of variances, I'm trying to say constant variances across globe. Now, the null hypothesis of the test, mathematically, the null hypothesis is basically going to be the variances are the same. While the alternative is going to tell you not all variances are equal. And you know what? You know what we want? What we basically need, okay, in order to validate our model is when we fail to reject the null hypothesis. Okay. Now, I'm going to walk you through an example right now. We are trying to compare the longevity. Okay. We want to compare longevity across, treatment group. Okay. We have different kind of treatment group, like AIDS pregnant, AIDS virgin, and so on like that. Okay, go ahead.
Your slides aren't changing.
Oh, the slide is not changing, right?
Correct.
Oh, okay. Thank you so much for confirming that. Give me 1 second. Somebody said, call my attention to this. My slide is not changing. For those who are attending online, give me 1 second. I'm basically gonna do that again. Now, can you confirm this to me now, whether it's changing? Is it changing?
We just see the title slide.
Oh, only the title slide? You don't see any movement, right?
No.
Okay. Let me see. What's going on? What about now?
Now we can see it changing.
Now it's changing, right? Okay, I'm
Yes.
also going to do this. I want to see whether it's still going to be changing. What about now? Is it changing as well?
No.
Oh, it's not changing now. Okay. I think I basically know why. Maybe I'm going to be, let me do this. Now it's changing now, right?
Yes.
Oh, okay. I think I'm going to make it that way. Thank you so much for observing that.
Thank
Okay,
you.
now I'm here. Okay, we have a food fly cell data set. Okay, and we basically want to compare longevity. The longevity is actually the response. And we have the treatment, okay, which is one categorical factor. We got some levels of that. We basically want to compare longevity, okay, at different levels of treatment. I actually, this is in the data set, this is the 4, 6, okay? this is the last 6. I see with the tail into that, but that is the last 6. Okay, now this is the code in R. If you basically want to have access to the data set, my TA is also going to walk you through this this week. Now, this is the code. Now, what am I doing here? What I'm actually doing here, I want to perform a Levine test. Let me tell you, if you want to perform a Levine test, you basically need to load a package called CAR. Okay, then you're going to write Levine test, longevity on treatment. You can see that the response is longevity. The treatment is basically the factor. Okay, as you can see. Okay, now what is the p-value now? What is the p-value telling you now? The 0.7419 is greater than the level of significance of 0.05. And what does that mean? It basically means you're going to fail to reject the non-hypothesis. Failing to reject the non-hypothesis actually means the homogeneity of variance hold. Okay, homogeneity of variance assumption hold. Is there anyone who have any question with that on how to conduct a Levine test? Is there anyone? Okay, you guys are good, right? On how to conduct a Levine test. Okay, the next thing I want to do now, I want to go into multiple tests. Now, let me tell you this. Why is it that, what if somebody asks you this question? Why is it that we cannot, why we have 3 groups? We want to compare 3 groups. Why do we need to use analysis of variance? Why can't we just conduct independent why can't we just compare 2 groups? In statistical analysis, we can compare whether there's a significant difference between 2 groups, right? Like you conduct a t-test. Why not conducting a t-test on a pairwise comparison? Why do we need to go for analysis of variance? Then I'm going to tell you why we need to go for analysis of variance and why we do not necessarily need to conduct a pairwise test, which we know as t-test, because if I have 3 groups, okay, and I want to compare a pairwise t-test, the number of comparison is basically going to be 3. Okay, and you know what? I'm going to show you why, the reason why we can't just conduct a pairwise test like that, because it's basically going to have effect on type 1 error. Okay, you're going to see now. Okay, now let's first, this is where the problem starts. If you look at the code I'm showing you now, we basically want to conduct an analysis of variance test. How many groups? We got 5 groups. That's why the degree of freedom equal to 4. Okay, the treatment is categorical with 5 levels. We basically want to see whether longevity, the average longevity is actually the same in 5 groups. Okay, and look at the p-value now. What is the p-value telling us? The p-value is very, very small, right? The p-value is very, very small. It's basically less than a 0.05 level of significance, right? Which is trying to tell us we're going to reject the non-hypothesis. What the non-hypothesis is basically telling us is that there is no significant difference in the average longevity of the 5 groups. Okay, while the alternative is going to say that is not true. But right now, we're rejecting the H0, and because of the fact that the p-value is very, very small. And let me tell you this. In analysis of variance, when the non-hypothesis is rejected, then we basically going to conduct a further analysis, because the analysis of variance cannot tell us where the difference lies. Okay, but the analysis of variance is only going to tell us whether there's a significant difference among the group compared or not, but it's not going to tell us which particular pair of treatment or levels of treatment where the difference lies. And what are we going to do? We need to conduct what we call, multiple comparison tests. But let me tell you this. We got 3 types of multiple comparison tests. The very first one is what we call the Fisher LSD. The second one is what we call the Bonferroni adjustment. And the third one is what we call the Turkey HSD. In this class, I think I've walked you through the Turkey HSD, but what I basically want to tell you today, I want to tell you situation where each of these comparison tests would be appropriate. I'm going to say that again. I want to tell you situations where any of this is appropriate. Okay. Now I'm going to start with, if you want to use any of this, basically, what are we trying to do? We know different is this, as indicated by ANOVA result, but we basically want to know where the different lies, putting into consideration or HPR of treatment group. Okay, now what we now want to do is we there are two ways we can do that. We can construct a confidence interval, and not only that, we can actually look at the p-value of the difference between the two groups. I'm going to say that again. If I really want to investigate where the difference lies, we can actually construct the confidence interval, and that would be simultaneous confidence interval, because depending on the numbers of comparison, if I have 10 comparisons, the number of confidence interval will be 10. And the numbers of p-values will also going to be 10. Because at each test, we're basically going to take a decision. Okay, now I wanted to give you the sense of what we want to do. When I say the confidence interval, when I say Y bar, I bar and YJ bar, probably I'm only looking at the difference between two categories, the means of two categories at a time. That's what I'm trying to do now. Then plus or minus margin of error. But let me tell you this. When I want to use whether the Fisher is, LSD, or I want to use a Bonferroni correction, or I want to use a Turkey HSD, I'm actually going to make use of this formula for confidence interval, but the only difference they're going to have is the margin of error. The margin of error of each of the multiple comparison tests are not going to be the same. But there is something that will be the same all the time. I'm going to say it now. There is something that will be the same all the time. This guy is always going to be the same. The Y bar I minus Y bar J, which we call the point estimate of the difference between two groups. They're always going to be the same. But you know what? When you look at the Fisher LSD, when you look at the Bonferroni correction, when you look at what is it called? The Turkey HSD, of course, the margin of error will not be the same. Okay, now I'm going to show you now. Let me start with the Fisher LSD. Now, right now, we use Fisher LSD where the non-hypothesis and analysis of variance is violated. And like I said, when the non-hypothesis and analysis of variance is rejected, and we want to know where the difference lies. But let me tell you the problem with the Fisher LSD. I'm going to tell you the problem with Fisher LSD. I'm also going to tell you how to compute the Fisher LSD. Now, the problem with the Fisher LSD is this. I'm going to show you now. If I actually have these numbers of groups, give me 1 second. Let me get the marker. Okay, now if I have 3 groups, that means K equal to 3, right? How many comparison tests is possible? That will be K combination 2, which is going to be 3 combination 2, right? Combinatorial analysis, which is basically 3 factorial, 3 minus 2 factorial, 2 factorial, which is going to be 6. It means my M equal to 6. Okay. Now, let me see. Sorry. Not 6. This is 6. 1, 2. Okay. My M equal to 3. Okay. Which means I'm basically going to look at between A and B, B and C, and A and C. How many tests? The number of comparison tests is basically going to be 3. Now, let me tell you the disadvantage of using the Fisher LSD. The Fisher LSD does not control the family error rate. It only it controls the family error rate, but to when the number of tests is more than 3, okay, then the Fisher LSD is not appropriate. I'm going to say that again. When the numbers of comparison is more than 3, okay, the Fisher LSD is not able to control the family error rate. Okay, it only controls the individual error rate. Now, I want you to listen to this. Let us assume that the null hypothesis is true. Some of you have been asking me a question. How do we get the level of significance to be 0.05 that we use all the time? When the null hypothesis is true, let's assume that HO, okay, is true. Okay, if you conduct 20 tests, let's say you conduct 20 tests, even if the null hypothesis is true, you will find at least one significant result. What is one significant result? Can somebody press calculator now? What is 1 divided by 20? Somebody should work it out. 1 divided by 20, what does it give you? That should give you 0.05. That is how we got the 0.05. Is 0.05, which is the level of significance, is the maximum probability of committing type 1 error. What is type 1 error? The type 1 error is when you reject the non-hypothesis when it is true. And that was why I told you from the one. In statistical analysis, if we don't have analysis that is error-free. Okay? Now, out of 20, okay, out of 20 tests, if the non-hypothesis is true, at least we will find one test that is significant. What do I mean by significant? At least we find one test that is going to tell you there is no significant difference. I mean, there is significant difference. That's what we call significant test. I'm going to say that again. If the non-hypothesis is true, what do we expect? When you conduct 20 tests, in each of the tests, that shouldn't be any significant, right? But that is not going to happen. Even if the non-hypothesis is true, you will find one test where significant is this. And let me tell you this. If that will now be the case, if that is going to be the case, okay, what is the probability of committing type 1 error? It's going to be 1. If the probability of type 1 error of type 1 error equal to alpha, then the probability of not committing that, will be 1 minus alpha, right? Okay, now if you take a look at this, 1 minus 1 minus alpha raised to the power n. If you take a look at what I have here, this is the probability of committing, at least the probability that if the non-hypothesis is true, the probability that you will find a single significant. You'll find a significant. Now let's take a look at this. When you have, let me say m, when m equal to 20, for instance, okay, and you do, and maybe your alpha is 0.05, okay, and you want to use a Fisher LSD, okay, the probability of committing type 1 error will be more than 0.05. Let us try it. It's going to be 1 minus 0.05 raised to the power 20. If you use a calculator, I'm afraid this may go to 0.64. This is far more than this. And that is a weakness of Fisher. Okay, that is a weakness of Fisher. Because of that, the problem with Fisher is too liberal. Liberal in the sense that it induces false positive. What do we mean by that? The probability of false positive, when I say false positive, where you are not supposed to have a significant result, the Fisher is going to tell you it is significant. You know why? because as the numbers of comparison increases, what happened to Fisher? As the number of comparison increases, the probability of committing type 1 error will be going up. Look at that. And what do we expect? We expect that to be 0.05, but it's not going to be 0.05 anymore. If you start plugging in the number of tests here, you're basically going to see it's going to be going up. Does that make sense to everyone? And that's why the Fisher LSD is not a good comparison test, because it induces type 1 error. It inflates type 1 error. And this is, if you want to know the magnitude of that, that is what I wrote on the board. Okay. Now, based on the example that we are working on, we're trying to see whether there's a significant difference between 5 levels of a particular factor, whether the longevity is the same. Okay, we conduct a Fisher LSD. This is what the Fisher LSD actually tells us. The confidence interval for the Fisher LSD, this is the result that we have, what I'm trying to tell you now. In the confidence interval, when it's between negative to positive, that means 0 is included. What does that mean? No difference, right? Okay, when it doesn't include negative, it doesn't include 0, then we say there's a significant difference. But you know what? The Fisher LSD cannot be trusted because it is too liberal. Okay, it is too liberal, and there is tendency for the probability of type 1 error to go up when the numbers of comparison increases, which I've demonstrated now. Okay, if you want to do that in R, using the R software, pairwise.t.test, longevity, treatment, p.adjust, none. When I say p.adjust, none, that I'm not adjusting, okay? That's a Fisher, and this is basically what you have. Take a look at that. When I compare one virgin with one pregnant, it gives us a 0.057. All these are p-values to be able to investigate whether significant difference exists between 2 groups or not. So take a look at that. Okay, this is how to do that in R. Now, because of the problem that we encounter with Fisher, then we now use what they call a Bonferroni correction. You know what Bonferroni correction does? The Bonferroni correction, the problem with Fisher is that Fisher was not able to control family error rate. Fisher only controlled the individual error rate. But you know what? The Bonferroni correction made an attempt to control family error rate. What do we do? What that is going to do is we needed to adjust for alpha. Okay, when alpha equal to 0.05, we're going to use the number of tests. M is the number of tests, right? I told you how you can get the number of tests. If you want to get the number of tests, okay, when you have K groups, what do we mean by K groups? Okay, when the treatment has K groups, if you want to determine the number of tests, you do this, K combination 2. Okay, this is a formula, K factorial divided by K minus 2 factorial, 2 factorial. Okay, that would give you the numbers of ways. This is basically M. Okay, now what I'm trying to tell you now, in the Bonferroni correction, you know what it's trying to do in an attempt by Bonferroni correction to correct the Fisher LSD. We need to find a new level of significance by using the numbers of pairwise comparison tests to divide the level of significance. What do you expect? The level of significance will be very, very small. The new one will be very small, right? Okay. Now, when you instead of you to be using a 0.05, your new level of significance will be 0.005. That is what it means. And another way you can compute that, you can use adjusted alpha will be equal to 1 minus 1 minus alpha raised to power this. Or you basically use alpha divided by n. Any of this can be used. Okay? Any of this can be used. That's a Bonferroni correction. But do you know the problem? with the Bonferroni correction. The Bonferroni correction is an improvement on, the official LSD, but oh my God, the Bonferroni correction lead to another problem. Bonferroni correction was able to control, was able to reduce the positive, false rate, but the Bonferroni correction lead to, a false negative rate. It, lead to higher false negative rate. I'm going to say that again. With the official LSD, okay, we have a problem of false positive rate, right? It increases the false positive rate in official LSD, but in a Bonferroni correction, why it make attempt to actually reduce the false positive rate, but the Bonferroni correction lead to another problem that we call a false negative rate. But let me tell you, it is mathematically proved and statistically observed there is no way you can adjust for false positive rate without affecting the false negative rate. Bonferroni correction adjusted for false, try to solve the problem of, created by official LSD, which is a problem of false positive rate, but in the process actually create another problem called the false negative rate. What do we mean by false negative? The false negative is where, you're trying to say there's no different, but different exists. Okay? And let me tell you this. If you're in a clinical research, when you don't see a significant difference between an effective treatment and a placebo, I'm going to say that again. Let's say you don't see a significant between an effective treatment and a placebo, and maybe in reality, an effective treatment is better than placebo. What are you going to do? What have you done? You will deny the patient of care because you don't find difference between effective treatment and placebo. Why? Because you use a Bonferroni correction, because if the Bonferroni correction will lead to false negative rate. The false negative rate in Bonferroni correction is going to be more. What do I mean by that? The Bonferroni correction, you're actually going to have a lot of, comparison. Even when different exists, it's going to tell you different does not exist. But let me tell you, when do we need Bonferroni correction? I'm going to tell you now. We need Bonferroni correction in a situation where we want to verify that different does not exist. Maybe we already know that different don't exist. For instance, when you look at a disease, maybe you want to verify that a particular disease is not associated with a phenotype. You already know in that kind of situation, you can use a Bonferroni correction. Because the Bonferroni correction has a higher chance of telling you, okay, that there is no difference. Though, what are we looking for? We're actually looking for no difference. But let me tell you this. If you're comparing it to chemotherapeutic treatment, and you basically want to use a Bonferroni correction, don't make a mistake. You need to test for more tests before you can use a Bonferroni correction. Because situation where I want to compare remission, I want to compare remission, okay, remission rate between two chemotherapeutic treatments, okay. I also need information about what is the survival rate, what is the quality of life score, and so on, and what is the complication rate. Okay, if I want to use a Bonferroni correction, now because of that, I'm basically going to say Bonferroni correction is highly conservative. Fisher LSD is too liberal. Bonferroni correction is highly conservative. Oh my God, I want to use this. Look at that. In the United States politics, we have two major political parties, right? The Democrats and the Republican. We have some Democrats that are highly to the left. You have some Republicans that are highly to the right. I'm going to say Fisher LSD look like Democrats who is far to the left. Why the Bonferroni correction is like a Republican who is far to the right. What do we need to solve a problem? Oh, somebody is going to be in the middle. Moderate, right? Moderate. Then Turkey is going to solve the problem. Turkey HSD will solve the problem, because the Turkey HSD is not too liberal and it's not too conservative. It is moderate. And that is the reason why when we are trying to figure out where different lies, when the null hypothesis is rejected in the analysis of variance, we basically want to consider Turkey HSD. Because the Turkey HSD is moderate. You know, in the United States politics, if Democrats are too liberal or if Republicans are too conservative, they hardly would they actually have, there's something that they call it, when they have a bill in the House and they want to have a bipartisan, support, they don't, the two parties don't need to go extreme. You get what I mean, right? That is what the Turkey is trying to do here. We solve the problem of too liberal and of too conservative. Okay. Now, you can see the difference. Now, this is a Bonferroni code. You see? What is the difference? P dot adjust, then BONF. When you're dealing with the FSD, you have P dot adjust equal to none, right? That is FSD. It means you're not adjusting anything. But now this is a Bonferroni, and this is the result that we basically gonna have. Okay, now let's go to Turkey. Oh my God, Turkey is coming to solve the problem. Why is Turkey coming to solve the problem? Turkey is not too liberal and it's not too conservative. Does that make sense to everyone? And that's why we go for Turkey. Now, this is the code now. If I want to know the difference between two PS, okay, we normally reckon with Turkey, compared to Bonferroni and the Fisher LSD. Okay, is there anyone who need clarification on how Fisher work, on how Bonferroni work, on how Turkey work? Is there anyone who need clarification? So like I said, okay, go ahead. Oh, is Turkey better than the other one? Is that what you mean? Yeah. You know why Turkey is better? Because it's not too liberal and it's not too conservative. Oh my goodness, that's a very good question. Why do somebody asks, why do we need, since we know that Turkey works, why do we need to use the other one? Now let me tell you this. We use Bonferroni in a situation where the emphasis is on the non-hypothesis. Non-hypothesis, maybe we already know there's no difference. Then the Bonferroni will do the job. With the Bonferroni, you are not likely going to have a false positive with Bonferroni. So in a clinical trial, like when you know that a particular disease, okay, is not significantly different. I mean, it's not associated with a particular phenotype. You already know even before you go to test, right? Then you can use a Bonferroni in that situation, because the Bonferroni, we always make sure that the non-hypothesis is true. But the problem with Bonferroni, that could be false negative. You get what I mean? Okay, so when the emphasis is on the fact that we want to verify, we already know that there's no difference, right? There's no difference. We already know, but we want to verify, because let me tell you this. If you conduct a 40 different tests, okay, I wanted to compute this. 1 minus 0.05 raised to power 40. This is going to give you like 0.87, which is far more than what? 0.05. Look at that. It's 0.05. So this guy here is the probability of committing type 1 error. The probability of committing type 1 error will go up when the number of comparison is very, very high. So in a situation where you know that there shouldn't be any significant difference, you already know, but you want to verify, then you go for Bonferroni. Does that make sense? Does that solve your problem? Okay, thank you so much. Okay, now the next information is about contrast. Some of you, we've just done a multiple comparison test. What is the difference between a contrast and a multiple comparison test? I'm going to tell you now. You know, whether, they say the difference is that in a multiple comparison test, you are looking at the difference between two levels. Okay. But in the contrast, let me give you this example. You're going to understand. You're going to understand now. No mitigation. Okay. No mitigation, fixed marks, and vaccination. How many groups do we have? 3, right? You know what I want to do? If I want to compare doing nothing with doing something, these two is doing something, right? Doing something, doing nothing. Doing nothing. What do we want to compare? We want to compare infection rates. Then you are doing contrast. The contrast will enable you to compare 2 levels at a time with another level. But in the case of multiple comparison, you can only compare head to head. But with contrast, I can compare 2 levels with 1 level, or 3 levels with 1 level. I can compare vaccination and fixed marks, okay, together. I can compare with no mitigation. Does that make sense to everyone? This is what we call contrast, okay, where you compare more than 1 level with another level. But the difference between that and multiple comparison, in multiple comparison, you can only compare 1 level with 1 level. But with a contrast, you can do 2 levels with 1 level, 3 levels with 1 level. Does that make sense to everyone? So that is what we want to do with the contrast. And you know what? If we want to do that, we need to assign weight. For instance, I want to compare this with this. I'm basically going to say half, and this is going to be -1, in such a way that when you add this together and this, the sum of the weight will be 0. That is why I say here, C1 plus C2 up to C that is going to be equal to 0. Okay, if I'm comparing 3 with 1 level, it's going to be 1/3, 1/3, 1/3, and that guy is going to be -1. Does that make sense to everyone? Okay, now what I'm showing you now, we have a standard error for contrast. Okay, and now take a look at this. In the example we're treating, okay, let's say we want to compare living with virgin females to living alone. But in the living with virgin females, when we say virgin female could be either 1 or 8, that means 2 levels, right? You now want to compare with living alone. Oh my God, this is a null hypothesis. It means the mean, you need the mean of, the 2 of them is for virgin, but different levels of virgin, half and half, and the other one, none, is going to be -1. Like if you want to see it again the way we write it, it's basically going to look like that. Look at the H0. Half, -1. You see that? So the hypothesis we are testing here, if I live with a virgin, but you know what? The virgin has 2 levels, and compare with none, then I'm doing contrast. Okay, if I want to find the value, the estimate of the difference, now, you know what I'm going to do? I'm going to plug in the mean. What is the mean for that level? 1 virgin, 8 virgin, and none. I'm going to plug in that. Now the sample values of the difference actually give that. Then I need to find the standard error. Okay, I need to find the standard error. Now, look at that. This is how to find the standard error. If you look at what you have, half, -1 is here. Half, -1, the coefficient. That's what I'm squaring here. Where do I get 219? The 219 is a mean square error from the ANOVA table. Let me quickly take it up. You're going to see that now. Give me 1 second. Hello, do you guys see the residual? 219, the mean square error 219.3. That is where it's coming from. Okay, now by the time you get the standard error, this is the difference. Then you're going to find the ratio. When you find the ratio, you have a T calculated. When you have a T calculated, we get the p-value. that value minus 4.3 is very high. The p-value is going to be very small. My TA is going to walk you through how to get a p-value for that. What does that mean? When p-value is very small like this, it means there's a difference between virgin, living with virgin, and living alone. Don't forget, there are two levels of virgin. You're comparing two levels of virgin with just one level of the other one. That's a contrast. Okay? So this is another one. You know what are you comparing here? You're comparing two levels with another two levels. Half, half, minus half, minus half. Look at that. Two level with two level. That's a contrast. You do the same. And at the end of the day, you get your result. Look at that. And you take a decision. We're going to continue from here on Wednesday. So now you know the difference between multiple comparison and a contrast. Okay, going to see you on Wednesday.